This is clearly a guy. Look, that's a kid. They're just holding on to the rope. If it's not, if that's the the spool and hook and all that, the spool thing, then why is that the spool thing too? Well, they can't both be they're the same freaking drawing I cut and paste.
And then the shadow is the water.
Okay.
I thought the triangle was his body.
Did you think he was like new stuff?
I thought that too.
That's crazy.
Wow. Okay. Look, I'm not going to work harder at these diagrams, and this one is just a kind of a copy of the original.
I thought he was wearing a dress.
Why is that a problem? Why do you assume a he? All right. A child of mass M is sitting at rest on a swing of length L. The parent pulls them back, making an angle theta with the vertical as shown in the diagram. The parent uses a force that is perfectly horizontal. Before we start the problem, a reminder that our definition of work, even the integral definition of work, includes in it the cosine of an angle, because this dot product reminds us that we have to take the cosine of the angle between the force and the displacement. But we're going to start running out of letters here when it comes to how we deal with angles. Theta is a placeholder. And although I tried to make this clear, I've tried to do this a lot, there are a lot of things that are just placeholders. You have to understand their meaning. In this problem, this theta at the top is the angle between the force and the displacement. But they're also giving us a theta to use, which represents the angle that the rope makes with the vertical, right? Two different angles. Now, I'm not going to replace the theta at the top because it only shows up when we calculate work. We'll wait till that moment. But any other angle, we might need to use a different symbol for. Now, the first question is a net force question. And I assume we are pulling the child back with a force and then holding them as we are in the picture, which suggests that at this instant, the net force on the child is 0. So can we name a force acting on the child? Another force acting on the child? I don't think there's a normal force. There's no surface in contact with the child. Tension? I'll take tension. Now, if you want to say that the platform of the swing is providing a normal force, fine, and call that an N. I understand where you're going with that. I'm just going to say tension. And anything else? The force of the parent, which we are told is perfectly horizontal. By rules of geometry, this is also theta. So, we're trying to find an expression for F in terms of M, G, L, and theta, and any other fundamental constants that show up. I'm going to say net force in the x direction equals 0. Therefore, F minus T sine theta equals 0. And net force in the y direction equals 0. So T cosine theta minus mg equals 0. Are we good? I don't feel like writing out all the components anymore. We know our trig, right? No, because I looked at tests yesterday. We don't know our trig. But I'm going to have to assume at some point or another I'm no longer teaching that part anymore. So I'm at that point, okay? If you don't know how you need to get help, come see me. But I am pointing out that we can eliminate t between these two equations. I think the easiest way to do so is to solve these both for the t portion, but leave our trig function intact and divide both equations to get that the applied force equals mg tangent theta. Any question about that? All right. Calculus, what? So I do want to point out that when theta equals 0, tangent equals 0, right? When they're just hanging there, no force is required to keep them there from the parent. When they're just straight down, like here. However, the force increases as I pull sideways, because tangent increases as I pull sideways. So when I'm asked to calculate the work done by the parent or the work done by gravity, you take your pick. The work done by the parent or gravity lifting the child by applying this force, or by gravity applying a force, that force is changing as the child is lifted. Now, if you find the net force done by gravity, the force isn't changing, but the angle relative to the motion of the child is changing. If we find the work done by the force, which we can, the force is changing and the angle relative to the displacement is changing. So either way, finding the work is going to require that we use the integral version of work to do so. So the non-calculus version, not so complicated. So we can do these out of order if you'd like to see the easy way first. So how about we do that? Question number, I guess it's 3, part A, or C, part 1. Find an expression for the height of the child above their lowest position as a function of theta and L. I want to demonstrate this, but anybody who's had this class already knows what I'm about to do and should have been able to tell me this before we started. And a bunch of you should know how to do this anyways. I'm going to draw 2 lines. One I'm going to call as my reference level, and one is the string. I'm going to duplicate the string, so I know they are both the same length, and I'm going to draw it in such a way as to clearly show that they are the same length, and they are, when I move one of them, an angle theta, the child is listed a distance h above the ground. Fair enough? All right. I'm going to focus on this picture for a minute. This entire length is L, as is this length. That is also L. Let me draw another reference line. This isn't the reference level, but can you get on board with the fact that this must also be H? Okay. Then how about this has to be L cosine theta? Do you see the triangle that I'm indicating there? This is the adjacent side of a right triangle with L as a hypotenuse. All good? All right. H plus L cosine theta equals L, because all of this equals the entire length, correct? So H equals L times 1 minus cosine theta. So commit that to memory. Shows up a lot. And you can see why I would want to expect you to see where this comes from. But if you pull something like this to the side, that's the height in terms of the length of the string and the angle. You don't want to have to prove this to yourself every time. Any question about that? All right. C number 2 asks you to figure out the amount of potential energy the object has, or the kid has, when they are here. Well, assuming the red line is the reference level, gravitational potential energy is mg h minus h naught, where h naught is the height of the reference level and h is our height relative to the reference level. So seems to me like the gravitational potential energy is going to be mgl times 1 minus cosine theta. That's it. That's the answer. It's not going to be that easy to do with calculus. But if you can follow me with the calculus, there's a reason why doing the calculus merits looking into. Okay? So, are there any questions about this one? Because if you didn't understand this, you need to stop me now. This is child's play and can definitely be all over the test. There's absolutely no reason not to. Release the kid swings downwards, it's got kinetic energy. You see that this is a kinetic energy problem and a potential energy problem all over the place, right? All right. So, let's talk about the work done. I'm going to come back to this picture, and I'm going to use it. So, for the time being, I'm going to take away the things I don't need that are in this picture because they're just going to get distracting. I'll leave that L there. I'll leave that theta there. Don't really need that. Don't really need all that. Don't need that. And I don't need that. And I want to remind you that the parent is applying a force in this direction. That's the direction of the force. Not sure you guys can see that, so let me make it easier to see. I hope. That looks exactly right. There. Darker. All right? Now, as the parent pulls back the child doesn't go that direction. The child is constrained because they're on the end of the string. So they can only travel in directions that are perpendicular to the string, which means the child travels this way as I pull on the string. Does everybody understand why? This is critical before we go further. If you don't, we need to talk about it. Okay. So to try and figure out that angle, and I'm going to just write this as dx for the time being. This is the small change in position for me pulling a little harder. That all okay? Kind of like right in line with what we talked about yesterday. Now, I'm going to extend this line a little bit here and extend a vertical and write that this is theta. You see that has to be true because they are corresponding angles, which means this is 90 minus theta because this is a right angle here. And that makes this 90 minus theta, which by the way is just theta, right? So have I done due diligence enough to prove to you that the angle the string makes is the same as this angle here? We're going to need that. So, let's move you over there. Work equals the integral of f dot dx. Now, this is the work done by me pulling back the child. This is not the work done by gravity. I would expect those two to be the same. So we could redo this problem for the gravitational force. I promise you it's going to be the same. But if you don't believe me, we can do this again. But let's start with this. I need to put this in terms that make sense. And one of the things I want to remind you about is we do need to take this angle into account. That's going to be cosine of the angle between them. I just tried to do due diligence to say that this theta is this theta. So are you guys okay with that? So I will now write this as force times dx times the cosine of theta, and we are now on the same placeholder for what theta means. Theta is the angle between the force and the displacement, which is the angle of the string. We just found an expression for that force, though. The expression for that force, if I recall, was mg tan theta. All good? Any questions about this? Now, the problem we have here is that our force is about theta, but x represents a small change in position. You understand that a small change in position is also going to be related to a small change in angle. Do you guys notice that? So if the position changes a small amount, the angle changes a small amount. So we either have to do this whole thing in terms of the position change, which means finding out how we would express theta in terms of x. Not even sure that would work. Or we have to write the whole thing in terms of theta. We're going to write the whole things in terms of theta, by the way, because it's the easiest way to do this. And I'm going to remind you of something that I know is not a reminder because you won't remember that we talked about it. But we did. A long time ago, we talked about the relationship between arc length and angle. We did so in the service of showing that V equals omega times R. Do you remember that a while ago? Good. Because what we said was arc length, a change in arc length equaled a change in angle times R. And we use traditionally S for arc length. That suggests that we could write this as ds equals d theta times r, where ds is a small change in position. Now, it's not delta x, because x is linear, and ds is an arc length. But if dx is really, really small, then dx and ds would be the same. Does everybody understand? Or at least accept? You don't have to understand, but can you at least accept that? And if we look at our picture, that's not really a big stretch. If theta changes a small amount, not like that. That as an arc length, oops, that doesn't work. As an arc length goes, that's going to be a pretty small, I can't even tell the curvature, can you? And we're doing this in special calculus land where that gets even smaller, right? So I feel very confident in saying that we can take dx and replace it with ds times r. But r is the radius of this circle, so I'm going to put L. Right? Isn't L the radius of this circle? Okay. Now, let's complete this. We're talking about the work done in pulling the kid from an angle of 0 to an angle of theta. Right? Now, this caused consternation in 5th period, and it's understandably so. These two are not the same, technically. Theta does represent the angle of the string, but this theta represents the angle that we pull the string to when we're trying to calculate work. This is a placeholder for any angle along that path, but this represents the angle that we are going to pull the child before we release them. They are technically very similar, but they're just placeholders for angles. If you don't like it, we can use a different placeholder. Do you want to use a different placeholder now? Then we will. So we're going to say, we'll leave those thetas intact, but we're going to pull them to an angle phi so that we have a different angle, a different thing. We don't know what that angle is yet. All right. Let's clean this up. And somebody let me write something wrong, and that's okay. I'm going to correct it now. ds equals d theta times r, but for whatever reason I wrote ds there, and I should have wrote d theta. So thank you for not correcting me, letting me find my own mistake. You're swell. I can multiply these things in any order that I'd like, but traditionally, now that we have established the integral, we need to make the integrand be everything between the integral symbol and the differential. So I need to move the differential to the outside. It's telling me what my variable of integration is. And I'm going to rewrite this in a slightly different order. MGL times tan theta times cosine theta times d theta. Evaluated from 0 to phi. Work done. Tan theta times cosine theta? Sine theta. Thank you. Because tangent is sine over cosine, right? So everybody's good with that? So let's just go ahead and work to the side. So work equals the integral from 0 to phi of mgl sine theta d theta. Does the mass of the child change as the child moves? Does g change as the child moves? Does L change as the child moves? MGL times the integral from 0 to phi of sine theta d theta. Now, none of this was technically calculus, although a lot of it is required if you're going to do calculus. Most of this was substitutions and careful looks at geometry. But I would say that that's a lot of stuff. Would you guys agree? Mm-hmm. This part is where the calculus comes in, no? Taking the integral has two parts. Find the antiderivative, then plug in my limits. This isn't a polynomial, though. We have to know what the antiderivative of sine theta is. But I mean, you either know it or you don't. In calculus, you'll get to prove it, maybe, or maybe they'll just say, "Here's what it is. Let's move on." I don't really know what they're going to do. I was required to prove it when I took calculus. And I don't remember anything about what that takes. But the antiderivative of sine theta is minus cosine theta. And that was a whole thing in fifth period too. Where does the minus sign come from? I don't know. It's just what the calculus people say. So, and it is true. The derivative of sine is cosine. The derivative of cosine is minus sine. It's just the way it is. If you don't like it, sorry, that's the way calculus works. There is good reason. It has to do with the direction of the slope. If you look at the sine function and you look at the cosine function, you'll see why. Because remember, the derivative is the slope. So you can look at it and find out why it's negative. But I digress. I'm trying to focus. So we are not done. We just did step 1. And by the way, I mean step 1 of the integral. If you don't like it, I know 22 minutes. It's hard to focus. I can see all of you starting to squirm and stretch. I mean, you've hung in there a long time, but 22 minutes is a long way. The second part of doing an integral is to put in your limits. So I have to put in the top limit and then subtract while putting in the bottom limit. So mg, and that's way down at the bottom, so let's bring it up here. mgl times negative cosine phi minus negative cosine 0. Work done. What is the cosine of 0? So this is mgl times 1 minus cosine phi, where phi represents the angle that we pull the rope to. Not a surprise, correct? Now, hear me out. Not terrible. We could have done this different. We could have found out how much work was done by gravity doing this. And if you like, we could. Want to see it? It'll go a little faster. Okay? So, to do this one, I have to point out that this is the angle between gravity and dx. Do you guys see that okay? And that angle is 90 plus theta. All right? Still want it in terms of theta. Okay, here we go. This will go faster, I promise, because we're going to do a parallel process. Work equals the integral from 0 to phi My force is mg. And my, I still have dx. My dot product will include the cosine. That's a cosine of 90 plus theta. All right? Everybody happy with that? Good. This equals, I'm going to do the same substitution I did before. I'm going to write this as mg times d theta times L times the cosine of 90 plus theta. That okay? There is a trig identity for the cosine of 90 plus theta. Yes, Matthias.
Why is it 90 plus theta? Not 90 minus theta.
Somebody want to give me a trig identity? No. I mean, otherwise we have to do the integral of cosine of 90 plus theta. We can do u sub, but I think there's a trig identity for cosine of 90 plus theta. Go ahead.
Cosine of 90 times cosine of theta minus sine of 90 plus times sine of theta.
Oh my word, is this really what they teach you guys?
Yeah.
There's such an easier one. Oh my word. Oh my word. I am so frustrated with all you people. And it gives us the negative sign, which is valuable. So we have the integral of mg times d theta times L times negative sine theta. This is still from 0 to phi. I'm going to pull out all of the constants and reorganize negative mgl from 0 to phi of sine theta d theta. And since we've done this already, I feel no need to repeat it, right? Excellent. So we get negative mgl times 1 minus cosine phi as the work done by gravity, which clearly is negative. Has to be. We're doing work against a conservative force, which is why the gravitational potential energy comes out to be positive mgl times 1 minus cosine theta, because the work done by gravity was negative, but potential energy is minus the work done by a conservative force. I know. We've lost about 7 to 8 of you already. I can tell. The eye rubbing, the looking desperately at your notes for any shred of something else to talk about. But I do want you to understand that this had to work out to be this way. The work by gravity is path independent. It's path independent. So even though the kid doesn't travel straight upwards, travels along this arc, the work done still has to equal the amount of gravitational potential energy the kid has. There's another force acting on the child. Why didn't it do any work? Come on, smart people. This is my smart class. So Matthias asked a question, but he wants to answer now. Should I? I mean, you're going to you're going to ask a question. Yes, and I expect you guys to say that. The tension force is this way. It is perpendicular to the displacement. It does no work. Certainly caused the child to travel in a curved path, but it itself did no work because it was perpendicular to the motion of the child. All righty. Now the rest of this problem is actually, well, easier. So, and I hope that you will agree. The child is released and swings down to the lowest position. What is the tension in the cable the instant they are released? Be careful here. I did screw this up in 5th period a bit. Tension, weight. The instant they are released, their velocity is 0, but their acceleration is not 0, right? They're going to instantaneously begin to change speed, right? If I want to figure this question out, like what is the tension, I need a way to do so, but you need to be careful. I'm going to set a coordinate system up that is aligned with the direction of the acceleration, and that direction is this way. That's the direction of the acceleration. Fair enough? Because they're not going to go straight down. They're going to go perpendicular to the cable. This is theta. All good? This is the y direction. So net force in the y direction has to equal 0. So T minus mg cosine theta equals 0. So T equals mg cosine theta. That's the tension in the cable. Net force in the y direction does not equal 0, it equals ma. So mg sine theta equals ma. It's just like an incline. So a equals g sine theta. We all good? Pretty straightforward. That was number 1. Number 2. So what is the speed of the child at the bottom of their swing? Well, I think the gravitational potential energy will equal the kinetic energy. So mgl times 1 minus cosine phi, I guess, equals 1/2 mv squared. I'm going to do the algebra fast, so you guys okay with it? Cancel out the m's, multiply by 2. V is going to be the root of 2gl times 1 minus cosine phi. All good? And at the bottom, the kid is going to be experiencing a tension force straight upwards and weight downwards. That net force has to equal ma. It didn't have to equal mac before because their velocity was 0. They had no centripetal acceleration, right? The velocity is 0, they don't require it, but we are moving now, so we need a centripetal acceleration. That's why the centripetal acceleration rears its ugly head here. And that looks to be tension minus mg equals mv squared over L, right? So T equals mg plus m times v squared up there, 2gl times 1 minus cosine phi, all divided by L. I'd watch this if I were you, even though you're packing up. The L's cancel. Do you see that? mg plus 2mg minus 2mg cosine theta. I distributed because by distributing, I can show that this is T equals 3mg minus 2mg cosine theta. It's better to go ahead and distribute and combine like terms and have a simplified answer. All right. Yahoo.